We are going to talk now about why do we need to use polar A product solvents for Sn2 reactions, for example, and why we use polar product for Sn1 reactions. So first, when we have Sn2 reactions, we have, say, I'm going to use a different pen. This contrast is not so good. Okay. So let's say that I have this, which is a primary alkyl halide. All right, so in that case, I need a good nucleophile. So typically, this reaction Sn2 or better, we said that before, for secondary, for primary alkyl halides, faster than for secondary, and almost do not happen for the tertiary. So now, what we need here is a good, strong nucleophile. So we need a strong nucleophile for Sn2. For E2, we need a strong base. So strong base, but remember that we may have reagents that are both strong base, strong nucleophile. And here you may have hydroxide, ethoxide, methoxide. Okay, so with those, you can have either one. Now, but we need those species to be able to attack here, the nucleophile. Remember that we have to do a nucleophilic attack here in the Sn2 mechanism. The nucleophilic attack happens at the same time of the loss of the leaving group. So, but again, we said that we need a strong nucleophiles here. So we use polar A product solvents for that. So imagine that now, well, we know that this is a polar bond, right? We know that. So we can draw this delta negative, delta positive. Now, this is a metal group. Let's do this. It's kind of bulky. Because this is delta positive, and say that I have as my nucleophile, say that I have sodium chloride, just not a strong nucleophile, but not a strong base. So typically this is better for substitution. So now, but this is a salt, like that. So a reagent like that, chloride will be your nucleophile. But this, the polar A product solvents are able to actually stabilize the counter ion. So notice the different charges. But the nucleophile cannot approach the carbon that here is delta positive. So in other words, this negative cannot get close to this one. So polar A products are good at solvating the counter ions, such as sodium or potassium, but they do not solvate, meaning surrounding the molecules of the nucleophile. That's your nucleophile. And because of that, this is available for the attack. So let's see what happens if we have, instead of a polar A product, which is ideal for Sn2, polar A product. This molecule is acetone. We have another video with more solvents, right? Now, but now let's say that instead I have, I'm going to erase this one here. Let's change the solvent now. And now let's analyze what happens if I try to do that reaction with a polar product solvent. Here I'm going to grab water, right? So we know, let's throw it this way. This part of the molecule will be delta negative, right? Delta positive. And we know that we have a network of hydrogen bond here, right? We can do that because, again, the oxygen is delta negative and the hydrogens are delta positive. Now, if you have a nucleophile, say that is negatively charged, and is close to that, now it can actually interact with these hydrogens. And it can do so. We can have, say, a solvation shell surrounding the nucleophile. meaning if this is your nucleophile, you have a sphere of solvation. In the case of water, we call that hydration, but it's like hiding that nucleophile inside of that bubble of water, so it's not as available to attack here. So that's why solvents that are polar products are not good for Sn2, in which we need strong nucleophiles. Say also polar product solvents, such as this one, can stabilize counter ions. So if this is delta positive here, delta negative at the oxygen. If you had something like sodium, then it can stabilize that. So in other words, polar products are good to stabilize. This is water, can stabilize the cations, the counter ions, or the nucleophile, the anions. So because of that, then we cannot use polar product. We're not going to be using polar product solvents for the Sn2 reactions. So now we're going to see what happens with Sn1 reactions. Now we know what they can do. We don't want polar product with Sn2 because it will be hiding my nucleophile here inside the shell of Solvation, and I don't want that. I want that nucleophile to be readily available to attack. And instead we use an Sn2 polar A product because those solvate well, they stabilize the counter ion, the cations, and leave the nucleophiles by itself, not solvated. So they're good for that. Now let's analyze what happened with solvation effects in the case of Sn1 and E1. Now, here we have to remember that both reactions, Sn1 and E1, happen with the formation of a carbocation intermediate. So the first step in these two reactions is the departure of the leaving group. So here, let's draw that. Let's do this. So tributyl bromide, this departs. And so that's a common step in Sn1E1. Here you form a tertiary carbocation. And remember, because of that, we learned that tertiary alkyl halides react faster than secondaries. Primaries, the not, unless we can have rearrangement. And we have videos on carbocation rearrangement if you need to review this. So now, the point is here, why do we use polar product solvents in the case of Sn1 and E1? So in this case, we're going to be using polar product. And we learned before that these can be water, you can have ethanol, you can have methanol, you can have ammonia. All of those will have hydrogens attached to a very electronegative atom, such as nitrogen and hydrogen. So let's see what happens. So I'm going to, by analogy to that, notice that here I did the solvation of a sodium ion. Well, I could do something similar with the carbocation. So let's draw that. This is a drawing I did before. And we explained that in the case of Sn2, we don't use the solvents because it will stabilize that by solvation, but the nucleophile and, say, the counter ions, if there are there. But now here your intermediate is a carbocation. Here I'm only, well, let's draw that. Now just say that this is that volume. Well, you can draw a sphere similar to that where you will have, this is positive, so the negative end to this dipole. Delta negative, delta positive. So you can have a solvation shell here. And what that does is it stabilizes the carbocation. And as you stabilize the carbocation, then much better, the reaction is faster. So because of that, to make that reaction faster, by stabilizing the carbocation intermediate, this is why you choose polar product. So polar product, remember, can stabilize both anions and cations. In this case, because you have a carbocation intermediate, you will use a polar product to stabilize it.